Hi, welcome to the dynamics tutorials. So with this problem we're going to look at angular momentum. Still looking at just a particle, and it's also a kinetics problem, so we're going to see how this particle responds to forces. So we have a 1 kilogram mass that's moving initially in a circular path around a central hole. The mass is suspended by a string, and the string has an initial radius of 2 meters. And then at some point the rope starts to get pulled in with a constant velocity of 1 meter per second through the hole. So we want to find the velocity of the ball at t is equal to 1 second, and the motion is all in the horizontal plane, so we don't have to worry about the force of gravity. So here's our free body diagram. We just have the particle, and then we have the force caused by the tension in the rope. And then we'll need to find the new radius of the rope when we're at t is equal to 1 second. So if we think about separating it out into radial and transverse coordinates, we can look just at the radial coordinates. So the radial acceleration would be 0 because the radial velocity is this constant 1 meter per second. So we'll plug in the 0 for AR, and then the radius would then be 2 meters minus the 1 meter per second radial velocity times the 1 second, which would say that after that 1 second we're at a radius of 1 meter. Then we can do our angular momentum. So we'll say that the initial angular momentum about point O would be our center hole here that the rope's being pulled through, plus the integral of any moments about point O gives us our final angular momentum about point O. There's no force to create a moment about point O because all the force is only in t, and t always points through point O. So the sum of moments about point O is 0, so the integral of moments about point O dt is 0. The angular momentum is going to be the linear momentum times the perpendicular distance, and there might be some radial component to the velocity, but the radial component always goes through point O, so we really only have to consider the radius that the particle's at and then the theta component of the velocity. So here's our initial 2 meters distance that we're at, 1 kilogram mass of the particle, and the 5 meters per second that we had for our initial theta velocity. And that's got to be equal to the new 1 meter radius that we solved for times the 1 kilogram times the theta velocity after it moves in. Both of these have counterclockwise motion, and so both of these are going to be positive. We can then solve for our final theta velocity, and we get 10 meters per second squared. 10 meters per second. And then the problem asks us for the speed, so that would be the magnitude of the velocity. So we'll do the r component squared, add in the theta component squared, and then take a square root, and we get about 10.05 meters per second. Thanks for watching.